Okay, hi guys. So we'll be continuing on seeing law of equivalence, wherein we'll be basically continuing on our Iodometric titration. Okay. So in the last lecture we saw that um, milliequivalents of CuSO4 could be equated with the milliequivalents of Na2S2O3 because the n factor of iodine in that case was not changing. That's why we were able to equate the two. Okay. So just continuing on the top of it, that we saw that whatever moles, so basically the reason why we were able to equate the milli equivalents of CuSO4 with the milli equivalents of Na2S2O3, the reason was the n factor of I2 was not changing. As a result, we were able to equate them. So we'll get back to that again. So let's again write the step 1 and step 2 for that. So step 1 was 2 moles of CuSO4 plus 4 moles of Ki produces CO2I2 plus I2 plus 2 moles of K2SO4. Okay, n factor here is 1 and n factor here is 2. This was the step 1. Now step 2 would be something like, or rather step 2 is 2 moles of Na2S2O3 reacts with I2 to form 2 moles of NaI and Na2S4O6. So here we know that again n factor here is 2 and n factor here is 1. This is the two steps which we saw in the previous lecture. So now all the millimoles of I2 which were formed in this reaction were used in this step. Okay, so simply we can write that millimoles of I2 from step 1 were used for step 2. Okay, so the moles would remain the same. So as the moles are remaining the same, we can write that, as we know that if we multiply it, if we multiply the millimoles with n factor of I2 in step 1, so this would be nothing but millimoles of I2 in step 1 multiplied by 2, and if we multiply millimoles of I2 in step 2 with with n factor of I2 in step 2, we would get millimoles of I2 in multiplied by 2. So this is nothing but milli equivalent of I2 from in step 1, and this is nothing but milli equivalent of I2 in step 2. And since millimoles of I2 in step 1 is equals to millimoles of I2 in step 2, or in other words, this quantity and this quantity are same, this implies that milli equivalent of I2 in step 2 would indeed be equal to milli equivalent of I2 in step 2. So now therefore we can write milli equivalent of I2 is step 1 would be equal to milli equivalent of I2 in step 1 of I2 in step 2. And now we already know that from step 2 we can write that, or from step 1 and step 2 we can write that milli equivalents of I2 would be equal to milli equivalents of Na2S2O3. Okay, and similarly we can write that milli equivalents of Cu of I2 in this case, or I2 produced in this case, would be equal to milli equivalents of CuSO4. So from step 1 and 2 we can write, since milli equivalent of I2 step 1 would be equal to milli equivalent of CuSO4 again step 1, and again milli equivalent of I2 in step 2 would be equal to milli equivalent of Na2S2O3 is step 2. Hence, from as milli equivalent of I2 in step 1 is equal to milli equivalent of I2 in step 1, hence we can equate the RHS part of both the equations. Hence we can say that milli equivalents of CuSO4 would be equal to milli equivalent of Na2S2O3 be equal to milli equivalent of Na2S2O3. Okay, so now let's discuss the law of equivalence. Okay, so now what about this case wherein the above part was a part of law of equivalence, it's just that I am writing the heading now, so it's better that I write this heading above only. So this is law of equivalence we are discussing. Okay, so now what we have in table is, what about the iodometric titration? This was iodometric titration in which we are using KiO3. So step 1 would be, as we are using KiO3 to react with Ki instead of CuSO4, which we saw in the previous case, we get 3 moles of I2 plus 3 moles of H2O plus 6 moles of KCl aqueous. So in this case, n factor of this would be 5. Why? Let's see the oxidation here. It is going from plus 5 to 0. Okay, and this is going from minus 1 to 0 as well. Okay, so n factor here would be 1. And if we see the second step, step 2 would be the I2 released here would be used to react with Na2S2O3 and convert products would be 2 moles of NaI plus Na2S2 S4O6. Okay, so here n factor of this would be from 0, it is going to minus 1 state. N factor here is 2 and n factor for this is obviously 1. Why? Because it is going from 2 to 2.5. Okay, so as you can see that the n factor of I2 in both the cases is changing. Hence we cannot equate, or rather not this one, this one. So what would be the n factor here? N factor here would be 5/3. Okay, and this is not the correct n factor for Ki. We don't need to know the n factor of Ki. Obviously it would also be 5 because there are 5 moles of electrons involved in this reaction. So it would be 1 over 5, not 5. These are 5 moles of electrons here. The balanced equation has a 5 here. I forgot to write the 5 here, which I am writing now. Okay, so n factor here would be 5. For I2 it would be 5/3. So we cannot equate the equivalents or number of equivalents of I2 in both the steps. Hence we cannot say that milli equivalents of I2 formed would not be will not be equal to, or we can say that milli equivalents of I2 formed will not be equal to milli equivalents of I2 consumed, or in other words we cannot say that they both are equal. Okay, and as a result we even cannot say that milli equivalents of Na2S2O3 consumed in the second reaction would be equal to milli equivalents of KiO3. However, the milli equivalents at the step level is still applicable, in the sense that for step 2 I am writing that milli equivalents of I2 reacted would be equals to milli equivalents of Na2S2O3. And for step 1 also I can write milli equivalents of I2 formed would be equals to milli equivalents of KiO3 reacted. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing a question or a two on the same or the iodometric titration. So till then, good luck and goodbye.